boring, not so funny, because those code is for demonstration only, may not behave as we expected. Okay. First of all, we will try to understand what is a kernel. So we have a summary here. Yeah, you remember the color scheme. The kernel color is this blue. And eventually, later in the course, you will see this blue guy, okay, will become wider, thicker, or deeper. And these yellow guys will eventually vanquish. Okay. What this figure is about, okay? This figure is telling you one thing. Process actually has two living places. Okay? So that's why I put it in the middle. Two living places. One place that is something that you already heard of. This area. This area is something that you already heard of, the code, malloc. You call malloc and you create dynamically allocated memory. Global variable, local variable when you create functions. And also the entire thing, we give a name here to it. We call it user space. That means that you are the user of the system. You write the program, you execute it, so the memory belongs to you. So we call it user space memory. How about this part? This part is kind of hidden. You never seen it. We call it kernel space memory. So what is the kernel space memory? Kernel space memory also related to this process. One of the items from the kernel space memory is released to you guys when we are having a first lecture. It's the PID. The PID, you never use it before you come to this class, right? The first time you heard of it is from this class. Oh, there's a PID. Actually, the PID is the identification number of this structure inside the kernel. So believe it, okay? Inside the kernel, there is a double linked list holding this kind of structure with a unique ID, and this is the PID. And here, we govern everything using the code. We call it kernel code. Okay? The kernel is a piece of code, very long. It's a main method, okay, a main function, I should say. It's a main function. It will create memory. Inside is so-called kernel space memory, calling malloc. They are just a piece of code that every guys can understand it because written in C. Okay? And some hard part is written in assembly language. But this is a piece of code. Now, this piece of code is governing everything inside the process other than this guy. This guy is under your control. Your control. The kernel cannot touch. The kernel is so powerful, but it won't touch this area. It's under your control. You write your program. Now, this part is done. And we will go into distinguish, okay? These two guys. And these two guys, I give a name. One is called user space and kernel space. Usually, I will keep the kernel space small. Okay, so that you understand that actually you can malloc from any memory. Unless you're running out of memory, then there's no way to continue the process. But as long as you have enough memory, you can call malloc. If you're using 64-bit CPU, you can call malloc indefinitely without stop. I will try now. Okay, yeah. So where can I try that? So this is my Mac. Okay, I will go back to my department. Okay, yeah, I love to do damage, you know. And this is 19, and 19 is being reserved. 17, good. So guess how many memory that system has. First of all, this is when you see this symbol, it means it's 64-bit CPU. Okay, if it's 32-bit, it will be I6686. I666, then will be 32-bit. There's 64-bit CPU. Now this command, free minus m, should show how many free memory in terms of megabyte. How many? How many memory? How many megabyte? Or how many gigabyte? Huh? You don't know how to calculate? Okay. Okay, this number 4, 6, 3, 3, x, 4. My hand is cold. Okay. Divide by 1024. 45 gigabyte. This computer. Okay, CS department. Okay, CS department has more memory than you can imagine. Some system has 256. Now what I'm doing, I will go to some hidden directory, write the following program. Hey, whoa, what happened? Someone put this test.c here. I call it testing. Okay, testing. No. Okay, so what I'm going to do, increment more. Okay, standard light main, and then okay, I know that you want to see the results, so I set up an I here 0, and then for I equals 0. Do you know that we can write for loop like this? Yeah. Okay, good. Printf %d I. Now this is not the end. Here we go. 1024 times 1024. You know what I'm doing? How many is 1024 times 1024? 1 megabyte. Huh? Wait, oh, sorry. 1 megabyte. Every time I get 1 megabyte. Okay? And if the malloc return now, I will say, okay, I give up. Okay? And then break. And return 0. So clearly, what is this? This is the infinite loop, right? The for loop don't have any condition. I love to write for loop as well. Okay. And I keep on loop, and I will increment. Then you will see how many megabyte I will allocate. Let's go, huh? See it again. And take a look at the 3 minus m. When these two numbers add together, is this close to this limit? Very close, right? This one add this one, these two add together. This is the hardest support for extra memory. And this is the system memory. When these two add together, it's quite close to this sum, okay? And where are the missing memory? Where are the missing memory? The missing memory here. That guy steals things, okay? I can run, right, very fast. I get 40 gigabyte of memory, but I cannot get the entire system because we have kernel space memory to stand in my way and forbids me to take his share. And I'm forced to die. Why I'm forced to die? Take a look at the program again. Testing. Actually, it's based on my implementation. I find that this equal to null. Then I say, okay, I give up. Actually, what is the meaning when I have null? Do you still remember how many of you have go through a proper training of having a malloc core? No, no one. No one knows that it will return null. Okay. Yeah, this okay. Yeah, I know about this until I'm a MPhil student. I also don't check. Okay, but when I become a tutor, I need to tell student. Then I have to check again. So there is code. I promised you guys to talk about this, right? What is this code? It's P error. P error is something that print the system think that that kind of error. So the system will give you the message that they think it is appropriate. And you can add any prefix. The prefix I will say wow, okay. Yes. Yep, just a prefix. Then I can it. Okay, so this is a program. Now I compile it. No problem. Run. Go. What is the cannot memory, allocate memory? Who say this? Not me. Not me. I am not the one to say that. Take a look at the program again. When I encounter error, so this definitely error. I can loop through so many times without getting null. But now, when I get close to the memory limits, I get the return null, and return null so happen to match this cannot allocate memory error. And who say this is using P error. P error is a system design stuff. The system gives you the warning. So you don't need to create this, okay? You don't need to analyze, why is return null? I have to flip some book. No, you don't need to flip books. You don't need to flip manual. Just ask P error, hey, why? Tell me, okay? And now you understand this. This whole piece of system memory and a droid there, this kernel space stand there and don't release some memory is for him to use. And this memory holding the structure of a process, maybe some of the accounting information for how long you have run that process, as well as it has codes. You have a codes hiding there. So we have this table with this table. This table is described this kernel space memory versus the user space memory. What is the storage inside there? Okay, so first of all, inside the user space memory, okay, it's a shared region. Shared region. This area is shared amongst the entire system. Okay, I am the one who launched the one malloc. I am actually trying to conquer every shareable piece of memory and allocate to myself. Okay, but the reality is actually there are some other processes running. So I'm actually just conquer the share area. And here it's not share. Okay, why I call it share? Because it's process memory, and process memory is not just for one guy. It's for many guys because we have many processes. Now, how about kernel? Kernel only have one kernel. Okay, the kernel is if a living things, but it contains codes only, as well as some data structure, including something more device driver. If you have written like Arduino, MCU, okay, they have drivers. Okay, actually, when you load the driver, you actually load the memory, load the code into the kernel. So that's why I don't know whether you have tried it before. If you're old enough, then you have tried this. You install some driver, usually in Windows. You don't install a driver, that's okay. When you install a driver, blue screen. Yeah, it's because it's directly inject code into the kernel. And what happens if kernel segmentation faults? No one will save you. That is blue screen of death. Okay, so the kernel is actually very powerful in the sense that the kernel code can access many things. It can access the user program code, kernel code. Okay, by whom? By kernel code itself. Okay, and what is the meaning of having these two areas? This area, why we have this, is because whenever we call system call, right? We ask the kernel for a service. How can I isolate the data structure for the kernel from the user? Now, this is the little secret here. First of all, you are running a code on your CPU, right? And there is a program counter, and the program counter originally pointed to the somewhere inside your code. Now your code says that you are calling Fox system call, okay? Then you have to jump from this arrows to here. So what is this green guy? This green guy is a piece of code inside the kernel. Okay, let's say there's a Fox system call, or in my example here, I write a get PID. They are both system call, and you have to go down here to ask this, hey, get PID code. How should I access the memory such that I can get the PID? I follow the code, get the PID, return it, and go back to the user space memory, just like a simple function call. Okay, and when you look at here, actually we can draw a diagram in describing this scenario. The diagram is looking from the CPU point of view. The CPU is running on user space memory as well as user code. Then I give an orange color. If the CPU is running on user space memory and user space code, kernel space code and kernel space memory, then it will be blue. So you can draw in this way, and you are the CPU and look at the code, and there's something like this. Why I draw it out like this? Because I want to tell you that in measuring a process running time, it's not easy. Because whenever you run some code, I don't know what is your training over the data structure course. Have you do a sorting by yourself? Then if you have done so, you understand how to write a program. First of all, you start with an input file, right? You take the input file. And when you take the input file, you have to read from file, okay? After you read from file, everything stored in memory, and you do sorting. And sorting purely is a piece of code that you don't touch any files. After you sort it, you write it back to the hard disk, then you will touch the hard disk and touch the driver. Now, if I look at it in this way, I can describe it in this way. Here, you start your sorting program. And the sorting program, you enter the file name that you want to pick data. So you will go down. Of course, it's not drawn in a ratio here. So you go down to take the data from the hard disk. And when you come back, you have enough data now. You do the sorting, because sorting is all happen inside the memory, user space memory. So it won't touch any kernel. After this, you have to write it back to the hard disk. Let's say there's the duration here. Then you start ask the kernel to serve you. And usually, this period are usually slow. Are usually very slow. Okay? So let's take a look at this program. So what is this program? I don't know whether you heard of it or not. This program is called time. It's the measurement of how fast or how slow that a program runs. Okay, so let's take a look at this demonstration. This demonstration is very interesting. Every time people look at this first puzzle, what is that? And then they find that those errors you have faced before. Okay, we call it, we already jumped to another chapter. Wait, did I start recording? Oh yeah, I have. Yeah, I'm afraid I didn't start recording. Yeah, don't start even tell me. Okay, so I jumped chapter already. Chapter point 2. Okay, so there is a program called time example. This time example, what it's doing is doing a BC for loop. Okay, and a BC for loop, we have a choice. So what is the choice here? Is whether I want to print something out. Okay, so look at the code. It's not funny. Let me run it. I forgot to make it. Okay, then this is a time example. Okay, so we have a choice whether you want to call printf or not calling printf. So let's take a look. What will happen if I call printf? So call printf, press a 1 here, then we'll call printf, and we'll keep on printing something until the end of the loop. Okay, yeah, it's kind of boring. Hey, I Control C it. Wait. Okay. So what if I don't? 0. See, so fast. It's slow. Now, looking at it is no fun. Okay. I will show you the reports if I run it using this command called time. This time command can measure how long the process runs. So we have 3 measurements. One is system time, SYS. Whether this program has go into the kernel and ask kernel for help. If it has, then it will contribute some time there. If not, you are purely running code that written by you. Then will be user time. And what is the real time? The real time is the moment that you start the program until it's end. Okay? So this is version number 1. We have a 0 there. Now, what if I print the printf out? Yeah, wait for some time, huh? Wow, very slow, huh? What is the limit that I set? Why it takes so long, huh? Yeah, should be ending right now. Wait. What is the limit that I set? Hey, come on, baby. Please stop. Hey. Okay, Control C. Okay. Let me take a look at the code. What happened? Example. Huh? So small. Huh? Why? Can you see anything wrong? I cannot see anything wrong. Can you see? Why don't stop? X. Let me compile it again. Am I running this right program? Huh? Run. Wait. It won't stop. Come on. Huh? You see something wrong? I cannot see something wrong. Huh? Can you see something wrong? What? Yeah, X is large, I know, but why it takes so long? 1, 2, 3, 4, 5. 1 billion times should be fast. Okay. Let me have 1 zeros more. Yeah, I just count how many loops, okay? The number of loops is not very big, right? Again. Oh yeah, this time it will stop, okay? Very nice. Go. Now this time I have a time. So it takes 2 real seconds. User time, that means the code that written by you, executed by that amount, and system time is this amount. Now compare to the scenario that I don't print anything. Do you know actually what happened? What happened? I have several questions concerning this report. Okay, now first ask you is it kind of important? Why user time plus system time is not equal to real time? Why? Very important questions. Why is that? Do you know? Can you guess? Just make some wild guess. Why these two guys add together is not equal to real? Real time means the moment that I press enter until it stops. Here also the same case. Maybe the granularity problem. Granularity problem means that you cannot show so accurately up to the, let's say, the 5 or 6 decimal places. But you can see the real time is smaller, is much larger than these two guys. Do you know why? No, you don't know why, okay? So let me give you, there are several versions of answers. One answer is when you do a looping program, right? It's supposed to be a loop for some time. You are not the one who can take the CPU for the entire period, right? So you will make ways for other processes to run. Okay? And that is the time that you sacrifice. But the time that you start the program until the end of it also include the time you sacrifice. So add together, it must be larger. This guy add together must be smaller than this. Okay, so this is just a necessary condition, not sufficient. For what? For the magnitude. What happened? The magnitude is so outrageous. Or you can argue like this, oh, because this program takes a long time, so that means the amount of sacrifice equally, proportionally become bigger. Yeah, this is nonsense, okay? Yeah, this is something really interesting to look into. Why it is so wide difference here is because of device. Device. So what is the device? I'm doing printing. So the device that allows me to print will be the screen. Okay, will be the screen. And consider the amount of things that I print out is so big. Okay, I don't say too large, but an already large amount of data. When I try to print it out, the printf takes some time to finish it, and the device cannot cope with the speed of the CPU. So when you say that I want to print it out, actually printf cannot take that amount. And printf will take some time when you call the printf. Between you call and its return, there is a time delay. There is a time delay. Okay? And you can expect that because when you take a look at the outputs just shown, if the printing time can cope with the CPU time, you've never seen anything. Just like, ooh, when it stops, right? But you can see it going out slowly, right? So that means that the moment that you call printf, and the printf return has time delay, and the delay forces the process to stand there and wait until it can take another loop. Okay? So device is very slow. What are the device including the screen? You wait for the keyboard. Keyboard of course slower. Maybe even something that you don't expect. Memory itself is a device. Okay? Later, not in this chapter, in chapter 4, we will also tell you that malloc is very slow. Malloc is very slow, so that Octopus, you know Octopus card, they invent their own version of malloc in order to avoid the slow bottlenecks. Okay, then my friend tell me. Okay, now here you can see this calling device definitely is a no-no. Don't call it so many times. That's why we can improve this kind of program in following ways. Let's take a look. Maybe you think of this, yeah, this is kind of a joke, okay, but really works. Okay, sorry. Take a look at this program. This program will look for the exactly amount of time or not. Will they look for the exact amount of time? Or I should say, these two programs, whether they will produce different outputs. They produce something different or they produce the same outputs. What can you say about this? Same or different? Same. Then how about the speed? If you have heard of what I just said, every time you call printf, you incur penalty in waiting for the device to finish. So that means if I reduce the number of printf, can I gain something? Let's take a look. Now this program is quite how can I say, it's just a thing. There's a thing in your mind, and then you find that, why I write that program 3 years before is so stupid. Okay, let's go. It's a it's a printf slow. Then will be this version. Slow means I print the x one by one. The fast, I print the x 5x at a time. Okay. So measurement time, and then the program is first have a slow version. This is the report. Okay. So maybe you will forget about this. So I make sure I copy it, and I use the hotkey again. Okay. Sorry about that. Is there any text editor? Gedit. Okay. So make sure I copy the report, because when I run the next version, it will gone. Okay. So this is the slow version. How about the fast version? Okay. Do a comparison. Oh yeah. Sorry. Then make it bigger. Hey, I cannot make it bigger. Okay. The tricks. This is the slow version. This is the fast version. You won't expect that it's a 5 times gain, okay? But is there any gain? Yes. Is there some gain? Here, there's some gain. Of course, it's scaled with the number of cycles. Okay? If I make it more cycle, then you will see the difference will become more and more horrible. Okay? So what can you say about after you know about this? After you know about this, just a report. System call actually played a very important role in your program. If you're clever enough, then you won't do this thing. You won't read a file byte by byte or character by character, right? Now you know that every call you touch the device, you pay a penalty. And the penalty is, I don't know whether it's linear or not. Let's believe it's linear. Linear to the time that you call. I mean the number of times that you call. It's not worth paying this, right? How about we change into this version? What is the version? I take every time a whole block, let's say this amount is 4K. 4K byte or 1 meg, okay? 1 megabyte, pull it out, and I tackle this problem in a memory layer on your user space memory. The memory processor is much faster than you touch the device in a byte by byte manner. Okay? Another version is just I mentioned. Okay, I mentioned as let's say you are a very good student. Okay, you believe everything that your lecturer tells you. They tell you that never hard code, so you malloc. And I see some people write program like this. Okay, and you won't believe that this program is a work from a GPA 4.0 student. Yeah, there was people with 4.0. Okay, yeah, was. Okay. Not anymore. Okay, let's say the function is like this, foo. Okay, and he is so not clever, it's dumb, that he know that he shouldn't do any hard code. So every time he do this, pointer, malloc, some space, and then before I call return, not 0, return. Before I return, 3. Okay, this is the in the middle is processing some files, okay, or some memory. It doesn't care, okay. What is the difference if I do hard code, okay? Because I was his FYP supervisor, okay. I'm supervising some 4.0 student. Of course, I have to be critical, because I said no, this sucks, okay. You change it, okay. After I change it, the performance gain is 20%. Just change this into a hardcode array. Okay? Hardcode into array. Don't use malloc and free. Okay? We expect that the input must not bigger than 2 megabyte. Why not we hardcode into 2 megabyte array? 20% gain. Instead of doing malloc and free. Yeah. Because malloc and free incur one device core memory. Okay? And of course, there's a penalty, and a penalty depends on how many times you call it. Okay? And if you do something like this and a full program, full functions, it's called 1 million times. It's not worth it. Not worth it. Okay? So yeah, although I became critical at that time, but they really appreciate it. I have 20% speed gain, okay? Really happened, okay? Really happened a lot, I would say. And you can do a revision over the codes that you have written throughout this 3 years or 4 years. Did you ever do this? Okay, if you do this, then if you have time, you can use a time program, time command, to measure whether you will gain something if you change to something hard code. Okay, and of course, in this course, I will teach you many ways to hard code. In a memory chapter, I will tell you some elegant ways to hard code, how to hard code so that let's say you have a recursion program, I can reduce the amount of a chance that you get segmentation faults like that. Okay, but this time it's not about segmentation fault; it's about speed. Okay, and hope that you will enjoy it and you will try later. And then we will come next week, talk about internal fog, and I will bring my PC so that I can do infinite fog. Okay? If you want to do it, yeah, do it together, no problem. Yeah, the worst case is we put your computer. Okay? No way to lose anything.